So here we're going to do transformations of functions. Again, guys, when you do transformations of functions, you're going to want to, once again, really master the concept of what the parent functions look like. Okay, and like we spoke in class, of course you can do a table of values, you know, your input and your output. Remember, f of x is just a fancy way of writing y. And you can have some set values for each one. 0, 0 being pretty much an important one. I would do -1. The absolute value of -1 is 1. The absolute value of 1 is +1. And you see that you get 1, 1, or -1, 1, and 1, 1. And again, you'll notice that it's a V shape. But you're going to have to learn that it's a V shape, and you're going to have to, I think, remember that. Because if not, you're going to spend a lot of time doing table of values, which we definitely don't want you to do. So if you're going to memorize, I'm just putting on here the most common, I would memorize these combinations, okay? And so you can do this every time without actually having a table. Because notice, for example, if I do an x squared, if I do a quadratic function down here, I can come over here and do my chart. But notice that if I do 0, it's 0. If I do -1, it's 1. And if I do 1, it's 1. And so you're like, wait, these are the same 3 points that I just did on the absolute value. So again, if you don't know that this is a curved graph, you're going to be drawing a V or something. And so they are very different. Obviously, where I can distinguish the differences is if I go to the next one, like 2, and I do 2 squared is 4. And I realize, okay, this is starting to go up a little quicker and it has this curve. But you don't really want to have to do the graph of that many. So for me, I just graph these 3 points and I give this the curve that I know it has. And same goes for all of these. Again, if I do square root, you know, some basic square roots, you know, x and y here. So again, the square root of 0 is... well, let me start with 0. The square root of 0 is 0. The square root of 1 is 1. And I would come over here to 4. I'd make x 4 and say the square root of 4 is 2. Now you might say, well, why aren't you using negative numbers? Well, because the square root of negative x, or -1, let's say, well, that's I, right? And so again, we're not dealing with imaginary numbers. So in the basic parent function, I start at 0 and I do x values greater than or equal to 0. So again, if I come here, 0, 0, 1, 1, and 2, 3, 4, 2, and you'll notice that your graph will take this curve. It'll increase very slowly, and it'll go on forever. Again, your domain and ranges we can talk about, but again, this is just the basic look of the graphs. When I go to the cubic function, again, you're going to see, look what happens. If I do 0, I get 0. If I do -1 cubed, it's -1. And if I do +1 cubed, it's +1. So 0, 0, 1, 1, and -1, -1. And you might say, well, geez, that looks like a straight line. Well, it is. Kind of those 3 dots do form a straight line. If you don't know the shape, then you have no choice but to keep going. You know, I would have to say, okay, well, what happens if x is 2? Well, then y is 8. And then all of a sudden you start to see, oh, yeah, this has a curve. It's not a straight line, it's a curve. But again, if you just memorize, you know, you do these 3 points, you do those 3 points right there, these 3 points, and you memorize that this is going to end up being a curve. It's going to have this little squiggly curve. And same goes for the cube root. Okay, so the more you memorize, the less you have to do tables and charts and stuff like that. Again, I could do the cube root of -1 is -1, the cube root of 0 is 0, and the cube root of 1 is 1. So 0, 1, 1. Again, we're back to saying, oh, is that a line or is that a whatever? Again, you know that this function looks like this. And so memorize that. The more you memorize your cube roots and your cubic functions and your square roots and your quadratic functions and your absolute value functions, the less you have to rely on tables of values, which you really don't want to do. Okay? So when we transform those basic graphs, we're basically just going to be shifting them. Okay? So transformations are basically just shifts of those graphs. Now, what kinds of shifts? Well, we can shift it vertically, meaning up and down, okay? up and down. We can shift it horizontally, meaning side to side. We can do a vertical stretch or a vertical shrink. We'll talk about that. And we can do a reflection, which means flip it over some line or some axis. Now, we're not going to have to make this, super, super accurate. You're going to have to do your 3 basic points and then do the shifts to those 3 points or the transformations. And that's going to be more than enough for us. So when you come over to here, you're going to see vertical shifts. Okay, so vertical shifts basically are an up and down shift of your function. Notice in these pictures you've got, here's your absolute value function, your quadratic function, your square root function, your cubic function, and they didn't list the cube root function, but you could also include that here, cube root of x, okay? And when you have that parent function, and all that's being done is a number is being added to it out here. Notice the number is being added outside of, away from the x. Notice it's not in the absolute value with the x. It's not being squared with the x here. It's not in the square root sign. It's not being cubed. And it's not taking the cube root. It is kind of apart from it. Okay, when something's being added to it or subtracted from it and it's apart from the parent function, the original, what this means is this is a vertical shift. And you're going to go, when it's plus, you're going to go up whatever this number of units is. When it's a minus, you're going to be going down however many, whatever value these units are. I'm not really sure what that is right there. I think that's a typo. Okay, so you're going to be going up or down with the vertical shift. So that's the first type of shift. Okay, up or down. Okay, plus, minus. So let's just do a couple of graphs with that. So what I'm going to do is I'm going to do in red, I'm going to draw the parent function. So this is, notice that the parent function, I'm always going to kind of mark it in yellow, okay? So my x squared, that's a parabola. I've memorized these main points, and I know that my parabola is going to look something like that. Now, when it says that I'm going to notice then the plus 2 out here, then I know that this means a shift up 2 units. So I take those 3 points that I initially had here, and I'm going to move each one up 2 units. And there I'm going to draw my new one with the same curve. And so the blue graph is the equation or the graph of the function they gave me. So it's just the original shifted up 2 units. Okay? I go to the second one, x squared minus 2, and once again, I know that this is my parent function, and this is the move that it made, or the transformation. I know this means it's going to go down 2 units. So once again, I start with my original 3 points, and I do my original parabola, and then I know each point is going to go down 2 points, like that, and so there's my new parabola. So this is going down 2 units. So the blue is the one that represents what they gave me. So again, if you know how to graph the parent graph, you just graph the basic parent and you just move your dots, move those 3 points you created. And that's why memorizing is so important. The next transformation we're going to talk about is horizontal. And horizontal is left to right changes. And notice what happened here. You had your parent function, right? You had your absolute value of x, but they added some number within the absolute value bars. So notice on all of these, you started with your quadratic here, your x squared, your square root of x, and your x cubed. And notice that what happened was the number they added wasn't outside of it, it was within it. And again, it would work for cube root as well. Same goes for over here. We started with our absolute value of x, our x squared, our radical x, and our x to the 3rd power. And then they came in here and they subtracted something from the inside with the x. Well, what this is going to mean is this is a side-to-side shift, and it's going to move in the opposite direction of what you see. So here, a plus means to the left, however many units, okay? And a minus means you're going to go to the right. It's a little counterintuitive, okay? But anything usually associated with x's is kind of opposite what you think it should be, okay? So it's going to be a shift to the left or a shift to the right. So once again, now we're going to do some changes here. Like the first two, if I notice, I'm going to try to identify what's the parent function here. Well, this is an x squared, so I know that's a parabola. But I had 2 added to it. But notice the 2 is inside of the whole x portion of it, and it's within the x squared. So I'm going to basically start with, I'm going to come over to here, and I'm going to do my original parabola. Okay, that's my first step every time. I've got those 3 points that I've memorized, right? Let me kind of do black, black, black. Okay, and now I see that this is a plus 2, but it's within the x part of it. And so this I know is going to be left 2 units. So I'm going to come over here and I'm going to shift each point to the left 2 units. And so here is my new graph. So I just went to the left 2 units. Again, I'll go to the other one. Again, this is the same concept. I start with my x squared. I know this is a parabola. And all of a sudden they did a minus 2. Well, I know minus 2 means I'm going to go to the right 2 units. And guys, this is a memorization thing. If you don't memorize it, you're going to be doing, you're going to constantly spend your time doing tables of values and graphing with a table, and it's just a real pain. Okay, so again, I start with those 3 key points, my parent function, and I know I'm going to move 2 units to the right. So 2 to the right, 2 to the right, and 2 to the right. And then here's my new parabola, shifted 2 units to the right. And that's it. That's as easy as it can get, guys. Now we're going to notice that we've got, this is going to have this, 1, 2, or multiple transformations here. So let's look at what we've got. I go to the next one, and I always try to identify my parent graph. And I see that my parent graph is x cubed, and it's a minus 1 away from the x portion of it. So I know that this means it's going to go down 1. So this is my original cubic function. Remember, I know it's 1, 1, 0, 0, 1, 1, and negative 1, negative 1. But I remember that this has a curve. So that's my basic, right? Let me put these in black. And then I know that from here, I'm going to go down 1 unit. So this one goes down 1, this one goes down 1, and this one goes down 1. And I remember to kind of follow the curve with my move. And that's the one. It's a little bit weird looking, but I did go down 1 unit. Okay? And so again, that's my new one. The blue one is always the new one. Okay? The red is the parent, the blue is the transformation. Sorry. Now when I come to the next one here, I'm going to look at this one and really kind of pay attention. And I realize that this starts out as a cubic function. But what happened is we added 2 here with the x, and then we added 1 outside away from the x portion. So each of these means something different. Plus 2 here means left 2 units. And a plus 1 here means up 1 unit. So they mean different things, right? So again, I'm going to start by graphing my parent function. So I have this, and I'm going to kind of do my perfect cubic function right there. Again, I have these little points, 1, 2, and 3 there. Okay, and then I know that I'm going to go left 2 units and up 1. So I'll start with the bottom one. I'm going to go to the left 2 and up 1. I'm going to go left 2 and up 1. And I'm going to go left 2 and up 1. Now again, I know the shape, so I know that I have to give this curve. That's going to be on you to do the shape, because unless you plot, 4 points on each side of the center and 4 points on the left side of the center, whatever, then, then you can kind of see your curve. But if you want to plot less points, you have to remember your curve. And so again, this was my transformed graph, was to the left and up, and that's exactly what happened there. So once you get used to it, I think you guys are going to do great. Now, the tricky parts, you know, come in when you start having obviously multiple things and you have the more challenging graphs. But again, you just keep doing what you've been doing. You quickly identify in your equation what type of function are you dealing with. This is a cubic function. We subtracted 3 with the x, and then we added 2 out here. So I know that this means 3 units to the right, and I know this means 2 up, okay? So again, I come here, here, and here, and I go up, and I go down, and then I do my shifting, right? So again, my points that I'm using are the ones in black, and I'm going to go 3 to the right, 1, 2, 3, and 2 up, 1, 2, 3, and 2 up, and 1, 2, 3, and 2 up. And again, I remember that I have my curve. So again, I went like that, kind of over and up, and that's my final graph. And then I do number 8. Again, I go back over to here, and I recognize what kind of function. Notice it's a basic square root function, and then what's happened is I've subtracted 3 within the square root, and I've added 2 outside. So again, I know this is going to be to the right 3 units, and it's going to be up 2 units. So come over to my drawing again. My basic square root, remember, is 0, 0, 1, 1, and 4, 2, and it's this basic curve. And again, that's why it's important that you kind of remember that. So you have these 3 points quickly that you can graph. And then I know I'm going to go to the right 3, and I'm going to go up 2. So each one of these is going to go to the right 3, 1, 2, 3, and up 2. 1, 2, 3, and up 2. And 1, 2, 3, and up 2. And so my graph is going to look something like that. So again, it's not perfect, right? But I know that that's the general idea, and my points are in the right spot. Now we get to what becomes a little bit more challenging, and this is where we start dealing with reflections. And reflections can be a little bit tough. So what happens is, again, notice that you have your initial parent function. You've got x squared, you've got your absolute value of x, you've got your x cubed, you've got your square root, and then notice all of a sudden you have this one here where you have your square root of x, but now you have this change inside. So notice this negative outside, 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 and then the change inside. And that change inside could also happen with, let's say, you know, negative x squared, like that. So you could also have, like at the beginning, you could have your x squared, but then the opposite sign is on the inside. So you can have the opposite or negative added to the parent function. When the opposite or the negative is on the outside of the parent function, what you're talking about is a flip or reflection across the x-axis, okay? When it's on the inside with the x, okay, then you're flipping over the y-axis. So let me kind of give you an idea of how and why this would look like this. Notice that when the change is here on the outside, what you're doing is you're getting your normal parent function, but then you're doing the opposite of it. Well, remember that this is really your y value. So your y value is really becoming the opposite of whatever x squared would have normally been. So let's think about that. If we have a table of values, or not even a table, let's just do our parent function, 0, 0, 1, 1, negative 1, 1. And here's the parent, right? I should probably do it in red for consistency, okay? But if I come over to here, and now I have, if x is 1, I know that x squared, right, is also 1. But if I do the opposite of x squared, then it's going to give me a negative 1, okay? So when x is 1, y is negative 1. So what's happening is my input isn't changing, but my output is, because my output's becoming opposite. So in that case, instead of my output when x is 1, instead of my output being positive 1, it's negative 1. When x is negative 1, instead of my output being 1, it's negative 1. And so I notice, wow, if my outputs change, my y's are flipping, that means I'm going to flip over my x-axis. If my y is positive, it's going to become negative. And so that's what that whole opposite means. It's just basically giving you the opposite output, okay? So everything will flip over. If I have again, an absolute value graph, the parent function I know looks like this. But again, 0 doesn't change, there's no opposite of 0. But then when I'm graphing the absolute value of x, right, I know that if x is 1, the absolute value of 1 is 1, but the opposite of 1 is negative 1. And so again, I notice, oh wow, it flipped over the x-axis. And I can do this over and over and over again, but basically that's what we're doing here. That's how we do our reflection over the x-axis. Now, in the other case, what's happening is, notice that I'm changing x, whatever my original x is, I'm flipping it, the sign, I'm changing my x value, so I'm making the opposite input and figuring out what output I'm going to get. Well, if opposite input, opposite x, is going to take me across the y-axis. So again, let's kind of write this out and envision this. Normally, if I have the square root of x, I know that that's 0, 0, square root of 1 is 1, and if I go over here to 4 and 2, this is my original graph of the square root of x. Well, if I try to do the square root here, if I try to do here the square root of opposite, well then here it's the square root of 0. Okay, that's easy, 0. Now what happens is I have to be selective with the numbers I pick, because if I do, if x is, let's say, 1, now it's the square root of opposite 1, well, that's an imaginary number. That's not even going to show up on my thing, right? So what I have to end up doing, any positive number I'm going to plug in here for the square root of negative x is going to give me a square root of a negative number, which isn't going to work. So I have to kind of go to the left side of the graph. So the opposite of negative 1, square root of 1 is 1. So when x is negative 1, my output is 1. If I do the square root, the opposite of negative 4, let me do 4. So that means the square root of 4, which is 2. So when x is negative 4, I get positive 2. And notice that my graph completely flipped over. So this is the square root of the opposite of x. So again, it's a little bit weird, I know, but whenever, again, the opposite symbol or the negative sign is away from the parent function, it's going to flip over the x-axis, and when it's within the x part of it, it's going to be a flip over the y-axis. So again, we come here and try to figure out what's happening in this thing. And like always, I'm going to quickly identify what my function is. I see it's a quadratic function. The negative is away from the x squared part, so I know this is going to be a reflection over the x-axis. And I know this is going to be up 2 units. So again, I start with my original parabola, because I know that's what this is, a parabola. And I'm going to start with my reflection. So I'm going to go to, I know I have to reflect it. So I'm going to reflect it, again, my positive 1 becomes negative 1 for both of these. And so this is the reflected version. This is just the reflection, okay? But then I notice I also have to go up 2 units. So let me do this in green. Up 2 here, up 2 here, and up 2 here. And so ultimately, the green is the correct final answer. Because again, I have to reflect it, then I have to shift it up. And so the green is the final graph of all of it. So come over to here, and I'm going to do the same thing. I sort of already did this one in the example, but again, the square root of negative x. Well, first of all, I know that the actual original problem is the square root of x, and I know that this minus part is a reflection. And because it's within the radical, I know it's a reflection over the y-axis. So again, I'm going to just draw my original parent function. I know it looks like this because again, I've memorized these basic points, and I know that what this means here is a reflection over the y-axis. So I don't need to do tables of values. I just know that this is going to reflect over. If this one here is 1 unit to the right, this is going to be 1 to the left. If this one here is 4 to the right, I know this one's going to be 4 to the left. And so that's how I do my reflection. And so again, I don't have to do the table of values if I know my parent function and I understand the reflections. And then this last one talks about something that we haven't talked about much, and it's vertical stretches and compressions. I don't think we're missing the slide on that. Basically, again, here, notice I have my x squared, and then you notice that it's 2 times x squared. So I'm going to show you, I'm going to do a table of values, and then I'm going to tell you what the effect is, okay? If you notice, basically, again, we're going to do our basic one, 0, 0. If x is 1, well, 1 squared is 1 times 2 is 2. And if it's -1, -1 squared is 1, and 1 times 2 is 2. And again, notice our parent function was 0, 1, and 1, because we know our quadratics. And then notice here that we have 0, 1, 2, and -1, 2. And all of a sudden, you notice that you have a parabola. It didn't shift up or down. It didn't reflect over any axis lines. What it did was it got narrower. Okay, it got narrower or skinnier. Okay, and we call that a vertical stretch. Vertical stretch. We'll talk more about that coming up, but a vertical stretch, it like got pulled up. Okay, it got pulled up from the x-axis. And so really think about it, you're basically saying that for the same x, your output is being multiplied by 2. So your y value is times 2. That makes sense. You're going to have a larger output for your input. And so that's how that would work. When I go to this one over here, again, I'm going to go to, I know this is my basic square root function. I know that what's done is this minus on the outside of it. And because it's on the outside, I know it's a reflection over the x-axis. So this one's a little bit easier. So again, this one I start with my key points. And I have that. And then I'm going to reflect it over the x-axis. So instead of +1, it's -1. Instead of +2, it's -2. And again, it looks like that. So this is the proper reflection. And then lastly, I'm going to show you another vertical change. And so the vertical changes occur when you have some number other than 1 being multiplied to your parent function. And in this case, notice that I'm multiplying by a half. Well, again, if I do just a basic XY chart, I know that if x is 0, a half times 0 is still 0. If x is, let's say, +1, half of +1 is a half. And if x is negative, it's negative a half. And so when I come to my graph to do my parent function, I know what that looks like. That's easy. But then here, notice I'm going to graph the transformed one with the half there. And I notice that I have 0, 0. When x is 1, my y is just a half. And when x is -1, my y is a half. And what you're going to notice is you're going to get a much fatter graph. Okay, so the half is going to be fatter, or not fatter, let me say wider. It's probably a better term, right? A wider graph, or fatter. And what that is that's called a vertical compression. Okay, compression or shrink. Okay. And so think of like you're going from the top down and you're sort of just pushing down on it and you're squashing it down towards the x-axis. And so that really is the graph. So whenever this value here is a number that is greater than 1 or less than -1, you're going to see, don't even worry about negatives. If there's a minus, think of it as a totally separate thing. If this number is greater than 1, okay, you're going to get this vertical stretch. If this number here happens to be between 0, let me call this, I don't want to call it x. Let's say if it's a fraction, okay, between 0 and 1, then it's going to be a shrink. And we'll talk more about that in the future, but that's how you do it. And again, you think about that. X squared is going to give you you put your input, you're going to get your normal output, and then you're going to cut it in half. So your y value is going to be half of what it would have been in the parent function. So it's going to be lower on the graph. Makes sense?